Today we're going to move into a major topic in calculus called limits. Limits are used extensively in most areas of calculus. The concept of a limit is this. And you'll see from some examples that I'll give you, is the value of a function the value of a function, that means the y value or the output. Now, when we talk about limits, if I say, what is the limit of such and such function, we're talking about the y values. We're talking about the outputs. So just keep that in mind when I say the word limit, it's a y value. It's the value of a function that is approached. Okay, this value is approaching a certain number as the input, and the input, the x value we're talking about, approaches. That's a big word in limits, is approaching. As the x value approaches a certain number. Okay, a limit, the y value or the output, that is the height of the function. Keep that in mind when you were looking at something graphically. The y value is the height of a function. I abbreviate function FCN. All right, so we're looking graphically sometimes at the height of this. Now we will evaluate limits of functions. So I'm going to say evaluate this function's limit. So evaluate limits of functions and study them from 3 different perspectives. Can you read that? Yeah. The 3 perspectives are called numerically, the second one is graphically, and the third perspective is analytically or algebraically. They both start with the letter A, analytic and algebraic. So sometimes this is referred to as the NAG process, N-A-G, NAG, like I'm going to nag you about lots of things. So that's kind of the words behind what a limit is, but it's really a lot easier to understand limits if we go through some specific examples. So that's what I'm going to do now. I'm going to give you a couple of examples to evaluate a limit. So here's your first example. Let's say I'm going to give you f of x and make that equal to x squared minus x minus 12 all over x minus 4. Well, some of you can already jump on this function and say, oh, I can probably simplify that or whatever. But we're just going to look at this particular function. We're not going to simplify it right now. And what I want to do is I want to see if we can evaluate f of 4. So if we have to evaluate f of 4, it's just a direct substitution, 4 squared. So f of 4 is equal to 4 squared, which is 16, minus 4 minus 12, all over 4 minus 4. And when we evaluate f of 4, we're going to get 0 over 0. And 0 over 0 is called an indeterminate form or an indeterminate number because you don't know anything over itself is 1, but 0 over anything is 0, but anything over 0 is infinity. So this is called an indeterminate form. Indeterminate, ATE, form. It just means that this is really not the value. 0 over 0 is not, you can't determine what that is. So what we're going to do is look at this from a limit perspective. First, numerically, from a limit perspective. Okay, when we look at something numerically, numerically means a table of values and when we look at a table of values, the graphing calculator will be very helpful in quickly evaluating these. So let's look at some XY values right off from the table in our calculator. So from a limit perspective, we're going to get something very, very close to 4, x equals 4, but we can't have x equals 4 because y will be undefined. It'll be 0 over 0. So we're going to look at x equals 3.9. Then we're going to look at x equals 3.99 and look at 3.999. So what we're going to do is we're going to get closer and closer and closer and closer to 4 from values that are less than 4. And then we're going to look at values that are 4.1 that are close to 4 but just a little bit above. So we'll look at 4.1, 4.01, and 4.001. So we'll look at the 1,000th place. So what I'd like you to do is grab your graphing calculator, and you can use the fraction bar if you want to on your calculator like I did, or you can just put parentheses around the numerator and denominator. After you get done putting this in your calculator, then I want you to go to Table Set, second window, and instead of auto, put the independent variable as ask. I think we've done this before. So change that to ask. That's with second table set. And then when you look at the table of values, it'll be blank. It's just waiting for us to put those values in so we can plug in those specific values of x. So we'll start out with 3.9. And when x equals 3.9, y equals 6.9. And when x equals 3.99, x equals 6.99. And when x equals 3.999, y equals 6.999. So hopefully you can see what the pattern is. This y value, it looks like it's getting close to 7. Well, now let's look at some values that are just a little bit above x equals 4. So we'll look at 4.1, and the y value is 7.1. And if we look at 4.01, 7.01, and 4.01 will give us 7.001. So what's happening here is when x gets closer and closer and closer to 4, from both directions, the y value is getting closer and closer to 7. So we write that as x approaches 4, x approaches 4 from both directions, from the less than and from the greater than direction. We call that from both directions. Y approaches, well, what value does it approach? It approaches 7. So this is the numeric way of finding a limit. You just get the x values closer and closer and closer to the value that we want. In this case is 4, and see what the y values are going to give us. So that's called the numeric way. The next thing we're going to look at is the graphic method. So graphically, what would this thing look like? So that's numeric. The next is graphic. So from the graphing perspective, when we take a look at this graph, when you press the graph button, it just looks like a straight line. So the values are, if we go back to table set, if we go back to auto, and after we change our mode back to auto and look at the table of values, it looks like X going up by single digits, Y also goes up by single digits. So we can graph this function 0, 3, 1, 4, 2, 5, 3, 6. 4 does not have a value, 5, 8. And so if you wanted to just do a quick sketch of this graph on your XY axis, you're going to go out to 4. And the y-intercept is 3. 0, 3 is where it starts. 0, 3, 1, 4, 2, 5, 3, 6. And it looks like it would be 4, 7. It looks like the height of this graph is equal to 7. So from a graphic perspective, the limit as x is getting closer and closer and closer to the value 4 from both directions, from the less than 4 and from the greater than 4 direction, it looks like the height of this graph is getting closer and closer and closer to 7. And then the last way is the analytical way. Analytically means also algebraically. So from the beginning, you probably notice that the numerator could be factored into x minus 4 times x plus 3, and it's all over x minus 4. So you can cancel those x minus 4s out, but this f of x value is only valid for x, all input except for x equals 4. The domain is all real numbers except for 4. So you have to kind of put this caveat off to the side that this is really the function y equals x plus 3, but x cannot be equal to 4. And if you do a direct substitution into x plus 3 into this particular function, f of 4 really does equal 7. But from the beginning we say this original function cannot have a value of x equals 4. But if we could, it would be equal to 7. So that's the third way, the analytical way. Oftentimes we're given functions that can't be reduced like this one can. And the only way that you could find these limits is using a numeric or graphic way. I'll give you an example that you couldn't use an analytical way. This is example number 2. If I want to find, let's say I have my f of x function that's equal to the sine of x over x. And if I wanted to find out what is f of 0, well, the sine of 0 is 0, and when x equals 0, this is going to be an indeterminate form again. Indeterminate form, because you don't know really what that could be. But there's no way to analytically reduce this down because the sine of x is not you can't factor it. You can't use a trig identity to replace it with anything. So you have the sine of x divided by x. So the only way you could do it would be numerically. So what we're going to do numerically is we're going to get some x values that are very close to 0, like negative 0.1, I guess we could start with, negative 0.01, negative 0.001. That's all approaching 0 from numbers that are less than 0. And then from the above 0, we could put positive 0.1, positive 0.01, positive 0.001. We're getting closer and closer to 0 with x values that are greater than 0. So let's see what this function looks like. We'll put y equals, let me get this stuff out of here, the sine of x divided by just plain old x. And we're going to go back to table set and we're going to do ask again. And the values I want are negative 0.1. Looks like y is 0.99833. Negative 0.01, it looks like it's 0.99998, and negative 0.001 you have to actually highlight this value to see that this is 0.999999998 and then a bunch of 3s. So 1, 2, 3, 4, 5, 6 9s. 1, 2, 3, 4, 5, 6 9s, and 8, and then a whole bunch of 3s. And then when x equals 0.1, you'll see the exact same numbers as you did with the negative ones. So 0.99833. If you put positive 0.01, you get that same number, and positive 0.001, you get that same value. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So what are the y values approaching? It looks like the y values are approaching 1 from a numerics perspective. So the y values approach 1 as x approaches 0. And then the other way to look at this is graphically. So when you press your graph button on this, it looks like when x equals 0, you could zoom in or zoom trig, I guess, on this to get a little better look at this graph. But it looks like when x equals 0, the height of this function is equal to 1, even though when you look at the table of values, when x equals 0, it's going to be undefined. If we go back to table set and do an auto on that, see those values, that x value equals 0, there isn't 1, but then all of these values are getting closer and closer to 1. So the graphic perspective looks like comes under and then goes above and comes under. In that height, when x equals 0, the height is 1 when x equals 0. All right. So those are the two ways we can analyze that function. Now to wrap this all up, I want to give you the notation for limits. How do we write these things? Well, we write these with the word LIM, that means the limit, and then we say underneath x approaches some value. I'll give you the first example, the example number 1. We had the limit as x approaches 4 of x squared minus x minus 4, minus 12, all over x minus 4. So the limit of that function is equal to 7, because as x got closer and closer to 4, this function got closer and closer to 7. But you cannot do f of 4 equals 7, all right? F of 4 does not equal 7, but the limit does equal 7. And here's your second example, the sine of x, the limit, as x approaches 0 of the sine of x all over x is equal to 1, because we saw numerically and graphically that that y value was getting closer and closer to 1 as x got closer and closer to 0. But you cannot say that f of 0 equals 1, because it doesn't. That's an undefined value. So I'll just put but here. And that's about it. That's your introduction to limits.